Welcome to 61D, the course where we teach you modern full-stack web development. My name is Aiden, and today we're going to be covering data modeling in a relational database. As a quick overview, we are first going to talk about the different database options out there, the pros and cons, and why most of the time I think you should use a certain type of database. Then we're going to talk about Drizzle ORM, which is what we're going to use to connect our TypeScript applications to our database. And finally, when we get into data modeling, we're first going to model a single table representing a single type of object within the database. And then we are going to figure out how we can relate together different types of tables. So for instance, you might have an author that has a lot of different posts on a blogging site, and we need to be able to relate those. So as I said, today we are just going to be worrying about modeling our data, and then later we will worry about actually querying our data and doing all kinds of other stuff with our database. And just to orient ourselves, for the last however many lectures, we have been talking about the sort of front-end user interface client that our end user uses to interact with our application. Now we're jumping all the way back to the database level, which stores the application state, all kinds of just, user information. The database is kind of the source of truth about our application. And then once we understand how to use each of these parts, we'll create an actual web server that connects them together. So with that, let's launch into what is a database. Basically, it is just a store with which we can write data to and then read data back from. Everybody intuitively understands what a database is going to do. If you think about something like Facebook, they need to store all the information about users, about posts, about who's liked what, who's following who. And for that, you need a database to store your information. There are several somewhat special purpose databases for specific unique applications. Noteworthy ones include graph databases, which are used for representing very large and complicated networks, which have a huge number of interconnected nodes. So something like a friends network within Facebook might benefit from a graph database because you have millions and millions of people who are friends with millions and millions of other people. And we also have time series databases, which are used for if you have some sort of sensor or something that you're going to get a new reading of every second or every millisecond, and it's just going to be consistently sort of spread out over time. There's special purpose databases for that. But most of the time, you're going to use a more general purpose database, which normally breaks down into two parts, being either relational databases or document databases, also known as just SQL databases and NoSQL databases. The main way you can understand the difference between a relational database and a NoSQL database is that relational databases have a schema that they enforce when you write data. So every time you try and add a user or a rating or a movie to the database, as we see here, it has to have the correct properties and they have to be of the correct type. However, the data in a NoSQL database does not have to follow any set schema when it is written. While this may seem like an advantage right off the bat, it does in many cases make it more difficult to reason about your application because you have fewer guarantees about the structure of your data. And especially if we want to use these data tables and the types that we can infer from them elsewhere in our application, we really need to have structured data when we write to our database. So that's why we're going to show you and recommend using relational databases unless you have a very specific reason to use a NoSQL database. The other issue is that there's no standardized way to interact with NoSQL databases. Common offerings such as MongoDB, Amazon's DynamoDB, or Google Cloud Firestore don't have one universal query language compared to SQL databases use SQL, and all major relational databases support the SQL standard. And moreover, revisiting the idea of having a schema, typically a NoSQL database is still going to enforce a schema. However, it's going to enforce that schema either when the data is read, or it's going to enforce that schema before the data is written by the application itself rather than by the database. Generally, this is just something that is really easy to move to the database and have the database handle. And for our use case specifically, databases are normally much more performant than our JavaScript application code. If we are asking the database to sort something, it's going to do it much quicker with C code under the hood than our JavaScript code ever could. Of course, there are some pros. You can perform migrations with zero downtime, which basically just means that since you don't have a schema, you never have to have your database wait a little bit while you modify the schema. And it's easier to split your database across multiple different instances so that you can share the overall workload. So what are the pros of a relational database? Most importantly is you get standardization. All relational databases can be queried using the same language called SQL, or structured query language, which has been around for 50 years. As a result of this, there's also just way more options for tooling, way better documentation, and more providers for relational databases because they're just so much more prevalent and more frequently used. As you can see the top 4 databases, according to a survey, are all relational, including Postgres, which we will talk about in a bit. And more importantly is the fact that they have generally a stronger guarantee about the type of data that you're going to write and read from your database. It has a schema, which means that when you write data, you know it matches the schema, so that when you read data, you don't have to perform any additional work because you already know that it's going to match your schema. Normally, data is read many, many more times than it's written. So anytime you can make your reads more efficient, even if it comes at the cost of the efficiency of your writes, it's normally a good idea. You also get foreign key constraints, which we will cover later in this video, and relational databases allow you to have strong transactional guarantees, which we'll cover in a couple lectures from now. But we'll revisit this idea of why we're choosing a relational database a couple more times over the next few lectures. But generally, you can think of it as, for the same reason we want to add types and add rules on top of JavaScript, is why we want to add rules, add a schema to our database and use a SQL database instead of a NoSQL database. It's easier to catch things at compile time than runtime, and it's easier to validate our data when it's written than to validate it when it's read. Now that we established that we're going to use a relational database, we have to figure out which relational database we're going to use. The 3 most popular variants are all open source, and they are all fantastic options, so you really can't go wrong here, but there are a few important differences. So you have SQLite, MySQL, and Postgres, which are all over 20 years old, super stable, super widely used technologies. The biggest difference is that MySQL and Postgres have to be interacted with as a server, as opposed to SQLite, which essentially just works as a single file which can live on a machine. The reason that you would want to interact with your database via a server is that then you can have multiple computers, or in this case, if you could have multiple instances of your application, they could all make independent connections to and read to and write from one centralized database. This means that when you are going to production, if you're ever going to have an application that potentially you might have to handle a large number of reads and writes and may eventually have to get scaled to multiple deployments, it's generally better to use either MySQL or Postgres. However, SQLite, which is actually what we're going to use today, is really great for some simple application or something that is only ever going to have to get interacted with by a single machine. And again, all the principles that we're going to cover today extend to all three of these options. So in summary, normally you want to use a relational database unless you have a very specific reason not to. We're going to recommend using Postgres for production databases. It just has a little bit more functionality and a little bit more flexibility than MySQL. And you can use SQLite for small applications or applications that are only going to have to run on a single instance or a single computer or a single server. And with that, let's start talking about how we're actually going to connect to our database and interact with it using Drizzle. We mentioned that you can use SQL to interact with your database, to create tables, to select from those tables, and generally do anything you'd want to do. However, even when we're using SQL, we still have a gap between SQL and between our TypeScript code. What we really want is we want to, if we have a table in our database that has a name, an ID, a Boolean saying, hey, is your ID verified, age and email, we want to be able to select from that table and eventually get a JavaScript object which is going to be typed with all of the correct properties so that we can actually use it in our application code. That is where Drizzle ORM comes in. It bridges the gap between our SQL database and our JavaScript, or in this case, TypeScript objects. What we can do is we can write queries using Drizzle's syntax to select from our database, and the responses from those queries will be properly typed using TypeScript. Drizzle is called an ORM, which is an object relational mapping. There are other ORMs that are also great options for TypeScript. Notable ones include Prisma, or also, actually all the others are pretty garbage. Basically, Drizzle or Prisma are your best bets. And what it lets you do is, again, you translate between your database schema and TypeScript. And the queries you write, it gets the response from the database and puts it into a nicely typed TypeScript object. So you can almost think of it as like a language translator translating from, Chinese to English in the same way that we're translating from SQL to TypeScript. Another important reason to use Drizzle specifically over other ORMs is the fact that it actually mirrors the syntax of SQL very, very closely. For instance, this is an example of selecting from a hypothetical countries table on our database. The Drizzle code on the left, we're going to say, hey, we have our database, we're going to select from a specific table, and we're going to perform a join, which basically just means that we're going to attach data from another table, and we're going to filter something. And as you can see, it very, very closely mirrors the actual SQL syntax that Drizzle is going to run, and it mirrors the SQL syntax that you could use if you were writing raw SQL queries. The benefit of this is that you have very, very little, there's very little black box voodoo magic going on in which you could get lost and not understand what is actually happening. When you learn Drizzle, you learn SQL, and if you already know SQL, you basically already know Drizzle, because it's just a few rewritings of the SQL syntax into TypeScript syntax so that we can get the proper types. In addition to modeling data, we also get a lot of other cool functionalities out of Drizzle. We sort of mentioned that we can use it for modeling our data and our database schema. We can use it for actually inserting and selecting data. We can infer TypeScript types from our database schema. We can run migrations. We get a cool little explorer for our data and a bunch of other stuff that is all built in and built around the Drizzle ecosystem. However, today, all we're going to be doing is modeling data. So now let's get started by looking at how we could model a single table, or at the very least model tables individually for our blogging application. Specifically, we are going to model a users table, a posts table, and a comments table. The database types that are available to us should be pretty familiar because most of them are pretty well expressed by TypeScript types. We can store text, we can store specifically integers or decimals, which are both going to be represented as TypeScript numbers. We store booleans, we can store arbitrary JSON, which are just going to be TypeScript objects. We can store timestamps, which are dates. We can store arbitrary blob data, which you could just represent with some kind of any type. And only in Postgres, not in SQLite, you can also do arrays and enums, which would be an array of whatever we're storing, or a type union. However, when we are modeling our database data, we do have to think about how the data differs between how it's represented in the database and how we might want to represent it in our application. A perfect example of the types of decisions we might have to make would be how to represent timestamps. You could think of it as a JavaScript date object, which is akin to the Postgres timestamp type. You could just store them as strings, which would be the equivalent of if we converted our date to an ISO string, or we could store a Unix timestamp. Unix timestamps represent the number of milliseconds that have elapsed since January 1st, 1970, and would be stored as a big integer. All of these methods can be converted between each other, and so they all more or less represent the same information. However, at the end of the day, we have to make a decision and stick with it for how we're going to represent data. This further comes in with things like booleans in SQLite. SQLite doesn't have a native boolean type, and instead it only stores an integer, which is either a 0 or 1, and throws an error if you try and set it to anything else. So it's just important to think about what are the differences between how something might be stored in your database and what it's going to be when it's read. Fortunately, the idea of an ORM is perfect for this. An ORM is a translation layer, so there's many things that we can do in our ORM to make sure that we're consistently reading data in a format that we can represent and use in TypeScript. For instance, JSON isn't natively supported in SQLite. However, we can just store it as a text string, and we can marshal and unmarshal the JSON from that text when we either read the JSON or write the JSON. Again, Drizzle, fortunately, will handle some of this for you, but it's important to think about what Drizzle is actually doing for you and what are the different ways in which you could represent the same pieces of information. Enough talking, let's actually write some code. Go to the description of this video and you'll find a link to the starter code. To get set up, all you need to do is copy and paste this setup script. Once you have it cloned, just paste it. This will create an environment file for you, which just points your database to the correct spot. It's going to install the dependencies, and it's going to create two SQLite databases for you. One starter database and one solution database. As always, everything is going to be already filled out in the solution folder, so you can take a look at that anytime you want, and we're going to be working in the starter folder. Also, there are a bunch of scripts which are either set to point to the solution database or the starter database. So anything that I do on the starter or the solution, you should be able to do with the other database as well. Anyways, Without further ado, let's open up our schema.ts file inside of starter. And this is going to be where we're going to put our definitions for all the tables in our database. So we're going to have a users table, we're going to have a posts table, and we're going to have a comments table. All right, so let's make our first table. For our user, we can say const users equals SQLite table. Then we need to pass in the actual table name that will be used in the SQL database. So we can just say users, and then the various different fields that we're gonna need. Every table needs an ID field. So for now, we can just have that be an integer, and we need to say that it is the primary key. What that means, and we'll talk about this more in a bit, is that this ID is what we're going to use when we are querying our user. We're going to specify the ID, and then the database can give us the user we want. And we can just say that we're also going to auto increment it, which means that it will automatically assign the next user to be the next higher integer. Next, we could just give them a name, which would be text, and maybe also an email, which would be text. And we could say age, which would also be an integer. Next, let's create a post table. So we can say const posts equals SQLite table posts. And again, we are going to have an ID as the integer primary key. And we could just give the post some content as text. And then you could do the same thing for comments. We could just copy and paste this table and say comments. And there we go. Now we have 3 separate tables, which are going to represent 3 different types of data. Forgot, we also have to hit export in front of all of these so that we can actually tell TypeScript we're going to use all these tables. And then we are ready to actually push this schema onto our database. So if you look into mydb.sqlite, it thinks it might be just like a text file that you can type in, but we're not going to do that. The reason that it looks like this is because it's completely empty. There's 0 bytes stored in this file. But in order to push this schema onto the database and have the database actually store the schema, we can run bun db push and then also say starter. So that's going to run this specific script, which is just making sure that we are using the correct config file to actually point it at mydb.sqlite instead of solutiondb.sqlite. So I could run this, and it's going to log, hey, we created this table comments, created table posts, and created table users. Next, we can actually open up a fantastic tool called Drizzle Studio, which lets us view our data in the browser and interact with it. So we can say bun db studio starter. I already had it running, so that should not have an error for you. But then we can open up local.drizzle.studio in the browser, local.drizzle.studio, and we can actually see our 3 tables. So we've got users, comments, and posts. And if we want, we can go ahead and add a user. You you can see that the ID is going to automatically increment by default for us, so we don't have to specify an ID manually. We can just add a name, so I could say Aiden. Aiden, hit enter. Email could be aidensunbury at berkeley.edu, and then age could be 55, like so. And then we can save, and now we have a user in our database. We can also see that when we try and insert users, our schema is going to be enforced. So for instance, if we added another user, say John, email, we don't have to specify an email, but then for an age, try to set hello and hit save one change, we are going to get the error that this string age is not a number. May seem like a frustrating thing to begin with, but these errors are actually a good thing because they make our application more predictable. We know that once we have written the data successfully, when we read the data, it's going to be of the correct type. We went over it briefly, but it's important to understand in depth the idea behind a primary key, or the ID. Every single record in a database needs a primary key, or an ID, and it has to be a unique value because the primary key is what identifies that specific record so that we can look it up. Under the hood, databases are powered by a specific data structure called a B-tree, which is shown below here. The way it works is that you have an ordering, a logical ordering of sorted IDs. So if you were imagining that each of these were IDs, and we wanted to check and find ID 250, we would go at the top, see, oh, it's not either 100, 155, or 226, and then realize that it is greater than 226, so we would proceed to the right. And then in this node, we would see it's not 270 or 190, but we would see it's less than 270, so then proceed to the left, and then find our item with ID of 250. This is really nice because if you have the primary key of a record, you can look it up very quickly. It scales at log n of the overall size of the database, which basically means that even if you have a database with millions and millions or billions of records, your lookups are still going to be very, very fast. However, that also explains why it has to be unique, because if we had tried to have two different values with an ID of 250, we wouldn't know how to differentiate them. The underlying workings of B-trees are covered much better by other people, so I'll leave some links in the description, but you don't need to understand them too deeply to understand how to work with a database. The properties of primary keys are always going to be the same. However, there are different ways that we can represent these primary keys. Similar to the idea of there's different ways we can represent a timestamp. We're going to cover a few options and showcase the pros and cons of each before we get to the recommended method that we're going to narrow in on. The first idea is just to have an incrementing counter, right? So something like GitHub issues, you create the first one and it gives you issue number 1 and then issue number 2 and 3. Obviously, these aren't the actual IDs since there's many more than 2005 GitHub issues in all of GitHub, but for a specific repository, you can sort of think of it as the individual ID. In certain circumstances, this is a good thing. Like, it's nice to know how many pull requests there are for a given repository. However, in other situations, using an incrementing counter like this might be detrimental because it is transparent, is the term. What that means is that if your user ever sees one of these IDs, it's going to expose information about your underlying system to that user. For instance, this ID shows us how many pull requests there are. In addition to being transparent and quote unquote leaking information, they're also guessable. So if you have some kind of system whereby you want IDs to be completely unguessable, using an incrementing counter is also not a good idea. Counters also have issues with concurrency, not within a single database, but if you have your database spread out across multiple different replicas. So for instance, you have one instance of the database on the East Coast and one instance of the database on the West Coast. It can create complexity whereby if you have a write which goes to one of the databases first and then the other database, and the different database received writes in the meantime, the two databases might disagree on the ordering on which certain things were created, and you could run into conflicts. However, there are a few benefits. One is that they are easily sortable, which, as we mentioned, overall your IDs are going to be sorted. And for performance reasons, you want to have your IDs basically be in order. So you want to insert it as 10, 11, 12, 13, not 10, 4, 17, 2, 6, 55. So they are sortable and they are easy to reason about. So they get a check for developer sanity. The reason why it is more efficient for your IDs to be what is called lexicographically sortable is a little bit beyond the scope of what we're going to talk about. But the key idea is that as you generate a new ID and a new ID and a new ID and a new ID, the later IDs should come after the earlier IDs when you're sorting them so that you store them in your B tree. What's the next option? We can also use what is called a UUID, or a unique user identifier. These are not transparent as they are completely random and unguessable, and you don't have any concurrency issues. UUIDs are deliberately designed such that generating two of the same UUID is mathematically pretty much impossible. However, you run into the issue that they are not easily sortable. Since every new UUID is 100% random, you're going to get inserts all over your B tree. You'll get one here, one here, one here, one here, one here, as opposed to saying, hey, it's 300, 301, 302, 303, which is going to degrade your performance a little bit. And you also don't get any sort of easy ability to reason about these IDs as a programmer. You don't get any information about what is it representing, how big is it, etc., etc. Fortunately, we can fix our sortability problem by using what is called a ULID, which is basically a UUID, except the first several bits are a timestamp, which means that as you insert a new UID, a new ULID, and then another ULID, and then another ULID, they will be sorted in increasing order, and you will never have a prior ID be inserted because this timestamp is forever increasing. The final thing that we can do to make IDs just easier to work with overall and get that final developer sanity checkbox is to prefix our IDs with the thing that they're actually representing. These are examples from the Stripe API docs. Stripe is a payment processing company. For their file IDs, they prefix it with file underscore and then some uniquely generated identifier, which means that you immediately know that it's different from their event object, which starts with EVT and then has their identifier. You can also notice they both start with 1. That's probably indicating that this part is a timestamp and just this N slightly later than this M, which means this event was probably created slightly later than this file. It's even more important with things like secrets. They have both a secret key, which you have to keep on your server, and a publishable key, which you are able to have available on your client. And you can imagine if these were just unique identifiers, it'd be super easy to mix these up. But the fact that one says SK test and one says PK test means that it's extremely easy to make sure you're using the correct thing. We wouldn't actually run into any of the concurrency issues that we talked about with auto-incrementing keys, but just for fun, let's swap this out and do text keys instead. So we can say text and say it's the primary key. And then what we're going to do is we're going to pass a default function, which is going to basically say, hey, what is the function we want to use to define our primary keys? So you can say default function, which takes a callback function, and we can just return a format string where we start off by saying what we want the prefix to be. So in this case, we could say user, and then say we are going to generate a ULID from that ULID library. So then if you want, you can go ahead and redo all the IDs. One note is that before we push this, we are probably going to have to delete any of the existing data because our ID types are going to be incompatible. So that's why it's important that you want to figure out what you're going to do at the start and stick with it before you start adding data and getting incompatible types. Then if you want to push those changes, you can again run bun db push starter. And it should show changes for you. I already ran them, so that's why it doesn't show changes for me. So far we have done a pretty good job creating our tables, choosing an ID that's going to be really nice to work with. However, there's certain things we haven't figured out how to do efficiently yet. For instance, we talked about how if you have the ID of a user, you can very quickly look up that ID and look up and find that user and find their name, their email, and their age. But at the moment, how would we figure out if a user exists with a given email? Currently, there's no good way of doing this. We would have to search through every single user and see, does that user already have that email? And clearly you can tell there must be some better way of doing this, because if you try and create an account on Facebook, they don't check a billion users to make sure whether or not that email is already in use. The solution is to create what is called a database index. What they do is they simply map whatever property we want back to the primary key so that then we can use that primary key for a quick lookup. Imagine we have our table of 5 users and we want to very quickly see, is there a user that has the email joclyn97@gmail.com? Instead of searching up through every single email, we can create and update every time a new record is inserted this index table. All it does is it stores all of the emails in a way that can be looked up in constant time. So depending on the database implementation, this could be another B tree, or it might be something like a hash table, which just allows for constant time key value lookups. And once we input this email, it is mapped to the ID, which then we can use for a quick access. It also allows us to enforce a uniqueness constraint. For instance, like we said, you could enforce that every user has a unique email by first creating the index, and then every time a user is created with a certain email, if the email already exists in the index, then you would throw an error and prevent a second user from being created with that same index. Drizzle provides us 2 different ways of creating an index. One is just a normal index, and the other is a unique index. So if we were to create a unique index on the email field, all we would have to do is pass this second set of options to our users table, where we pass the user, and we are going to create the email index, which is going to be a unique index with the name, user email index. And then we have to specify what property we're creating the index on. So in this case, it's user.email, like so. And then if we wanted to also create an index so that we could quickly search by names, but we didn't want to enforce everybody having a different name, then we could create another one. Say it is name index is just a normal index. Say username index on, user.name, like so. One final thing we can do to make sure that our data looks the way we want is we can also make certain fields be required, or not null is the technical term. Currently, we could create a user that just has an ID, but no name, no email, and no age, which doesn't really make sense. So if we want to enforce that we actually have a value for our name and for our email, all we need to do is say not null. Sometimes migrations are weird, and we're going to cover that more in a later video. So if you want this to get pushed properly onto your database, first comment out the index and just push the non-null constraint. And then you can uncomment these guys and push that. And there we go. We now, if we go to insert a record, so studio, when we add record, and if we were to have hello as a name and not put in an email, we would get our non-null constraint on the email property, like so. The final concept we're going to cover related to modeling data within an individual table as opposed to modeling relationships between tables is the idea of generated SQL columns. Let's say we wanted to mimic the functionality that Medium has, whereby it'll give you an estimate of how long it's going to take you to read an article. We could have a user manually input this, or we could manually calculate this within our application code, but it might make more sense to have SQL automatically calculate this value anytime the length of the article changes. So they probably have something more complicated that they do with their actual estimates, but a very simple estimate we could do is just use the length of our content in one of our given posts and divide it by some constant to say, hey, if it's a certain number of characters, it's going to take us a certain amount of time to read. If we accomplish this at the database level, then it's something that we remove from our application and just make it easier to reason about our data without having to make sure that both the content and the estimated reading time are updated, because as soon as we update the content, the estimated reading time will automatically update. So let's give this a shot. We can say estimated reading time is going to be a real number, and then we're going to say that it is a generated column. From here, we need to pass in a function which is going to tell the database how we calculate the value of this column. So we pass a function. We'll say that it is going to return a SQL string, which is just a type that Drizzle ORM gives you. And then we need to actually write some raw SQL to calculate what we need to calculate. This is the type of thing that it's very easy to ask AI to generate for you. I did that myself. All I want to do is I want to divide the length of my content by some number to figure out, hey, if I know how many characters it is, then how long is it going to take me to read that? So what you can do is say that we have a SQL string, which is going to take the length, capitals, the length of, we need to pass in the property. So it's going to be users.content. No, not users, my bad. Posts.content. Posts.content. And then this is going to be an integer. So to convert it into a real number, can multiply by 0.1. And then we can divide it by some constant, which I found on Wikipedia, which said that people read at about 863 characters per minute. So now, anytime the length of our content changes, so if we add something to it, remove something from it, then this estimated reading time is automatically going to get recalculated, and it'll be recalculated with our very performant database code as opposed to our not so performant application code. Final consideration to make before we push this onto our schema is different database paradigms support either virtual columns or stored columns. If you're using Postgres, it only supports stored columns, but since we're using SQLite, we have the option of either. Basically, we specify the mode. If we say it's a virtual column, then this value isn't going to be actually stored in the database. Instead, it'll be recalculated every time we query it, whereas if it's a stored column, it'll be recalculated every time the content changes. So let's save this, push it onto our schema, and then refresh, add a record. I'm going to copy and paste the course overview from the 61D website and see what it calculates on how long it tends to take. I'm going to guess maybe a couple minutes. And then like that, save. And it calculates that it would take 8 minutes to read this course overview, which I think is a pretty fair estimate. Now we're ready to start modeling relationships between the different tables in our database. For instance, if we have a post, who authored that post? When we have comments, what post do those comments refer to? The key idea that powers relationships in our database or relations are the idea of foreign keys. All it is you're storing the primary key of a different table. So for instance, we could have an airplane table and a flights table. The flights are going to want to know what airplane is servicing that flight, but the flight table isn't going to store all the information about the airplane, like the model and the brand, or if it has any wear and tear or anything like that. So instead, all the flight needs to do is store the ID of the airplane that it wants to associate with. This way, when we are querying flights, if we need to get additional information about the airplane that is servicing the flight, we can know where the airplane is and query that data and join it with our flight data, which we'll talk about later. The other important thing is that these constraints are enforced at the database level. This is the foreign key constraint that we talked about earlier. For instance, if you try to insert a flight with an airplane ID that doesn't correspond to an actual airplane, you'll get an error. This means that anytime there is an ID in the airplane ID column, you know for sure that that airplane exists, and if you were to query it, you would get an airplane back. There are three main types of relations we're going to cover. The first and simplest one is called a one-to-one relation. It's when a single table maps to a single other table. A perfect example is a country mapping to a capital. Most of the time, a country is only going to have one capital, and a capital is only going to correspond to one country. None of our current tables really make sense for a one-to-one relation because a user could have many posts and a post could have many comments. So really quick, I just created a user settings table, which would make sense for a one-to-one relation because one user is only going to have one set of settings. All we have is an ID and a theme property. In order to relate this user settings to an individual user, all we need to do is store the foreign key of the user on our user settings table. So to do this, we can just create a new property. User ID is still going to be text because all of our IDs are stored as text for this database. We probably want it to be not null because we always want user settings to be associated with a user. We don't want to be able to create settings for a user that doesn't exist. And then we are going to say that it references the users.id field, like so. So let's push this onto our database and check it out in Drizzle Studio. Here in Drizzle Studio, I have created a couple of users, and as you can see, we can already see the user settings relation is defined. So let's copy and paste one of these IDs and create some user settings for my user. Paste in that user ID, which is going to connect it to the correct user. And then I personally prefer dark mode, so I will put that and hit save. Now it's associated with that user, and for the user, I can click and see my settings. You can also see that if I try and add settings for a user that doesn't exist, so if I put in something random for an ID, and then, random for the user ID, and then try and say, light mode, and hit save, it's going to say foreign key constraint because this user ID has to correspond to an actual user that exists in the database. Funny enough, we're going to do the same exact thing when we want to start defining a one-to-many relation. That is where you have one parent, which can have many children. So for instance, one post can have many comments, but every comment has to correspond to just a single post. What we could do is on our comments table, just say post ID and say that it is text, not null, that references posts.id, like so. And if we push this, refresh Drizzle Studio, then we can add a post, test post, and add several comments to it. So post ID, is that? What a great post. Save, and then add a second comment corresponding to the same post. I did not like this post. And then we have many comments that are tied to the same post. Here, maybe we can refresh. Sometimes you have to stop and restart Drizzle Studio, but we did that, so now we have it showing where we have our post, and we can see the comments, and on our comments, we can see what post it corresponds to. But as you can see, we have the issue where we could add two different user settings for the same user. Save, and then I would have both light theme and dark theme as two different user settings. So to enforce that we only have one user settings, all we need to do is go back to what we did earlier and add a uniqueness constraint. So I will delete one of these so that this doesn't error when I try to migrate it. But on our user settings, this user ID, all we need to do is say .unique, and then Drizzle will create that unique index for us. So if we push it to the starter, you can see it creates the unique index. This is really just kind of a shorthand for what we did up here that will sort of name it for us rather than us being able to provide an explicit name. But once we do that, and once we probably refresh Drizzle Studio, if we try to add a new setting that corresponds to the same user, we will get our uniqueness constraint violated, which enforces we only have one set of settings for an individual user. Another point that goes on with this is that we only want to include the foreign key on one side of the relationship. We don't want to include our user settings on the user because it just makes it more difficult to maintain and keep both of them in sync. If something changes about our user settings, we only want to have to change one user ID to keep everything intact about this relationship. We have one-to-one relationships and one-to-many relationships. However, modeling many-to-many relationships is a fair bit trickier. If we're creating a blogging application, we want authors of blog posts to be able to be credited on multiple posts, and also we want an individual post to credit multiple authors. Let's take an example from the Next.js blog. They have a release or a blog post for Next.js 14.2, for the 15 release candidate, and for 15 release candidate 2. And you'll notice Delba is credited on all three of these, Zach is credited on 2 of them, and then Tim is only credited on 1 of them. So the relationship we need to model is whereby certain posts have many authors. In this case, all 3 of our posts have several authors, and all of our authors can be credited on many posts. But with our current sort of understanding, we can't really model this. We can't have Delba store something like an array of post IDs and our posts store an array of author IDs. Maintaining the referential integrity, or in other words, making sure that all those foreign key constraints are satisfied in an optimized way, doesn't really work when you're storing some large array of them. And that's just not really how our relational databases handle it in reality. The way we accomplish the many-to-many relationship is by cheating, and instead using 2 one-to-many relationships and introducing another table called a join table. In this case, our join table to connect posts to their authors is going to be called post authors. All we're going to store, besides the primary key of each entry, is the foreign key of the author ID and the foreign key of the post ID. And if we want to store any other information about this relationship, such as if some people are primary authors and some people are secondary authors, we could also store that on this table. Then, for every single individual relationship, every single relating of an author to a post, we insert a new record into this table. So for instance, to model the 3 posts that Delba is credited as an author on, we enter 3 records into the post authors table. All of them have Delba's author ID, but they have a different post ID. Then if we wanted to add Zach as an author to the Next.js Release Candidate 2 article, we could create a new record in the post authors table and have the author ID be Zach's author ID and the post ID be the Release Candidate 2 post ID. And then we can continue on and fill out the rest of this table to model the many-to-many relationship. Moving into Drizzle, we can actually implement this many-to-many relation. We can create a new table. We'll call it user posts. It is a SQLite table. And we'll call it user posts. And then if we remember, we need 2 foreign keys. We need the user ID, which is text, that is not null, and references the users.id. References users.id. And we have the post ID, which is text, which references the post.id. Posts.id. Now we have yet another problem with this many-to-many relation. How can we ensure that we can't import or can't insert 2 entries into the post authors table which define the same thing? We want to prevent creating 2 records that both tie Tim to our, here, make sure it's the right color. They both tie Tim to our Next.js 14 post. We can't enforce that the user ID is unique, and we can't enforce that the post ID is unique. Because, for instance, we want Delba to be able to be the author on multiple different posts, and we want all of our posts to be able to have multiple different authors. What we really need is we need a unique user post ID combination so that if you have the same user and the same post, then it will violate your uniqueness constraint. To do this, we need to create what is called a compound primary key, which simply means it's a primary key that is derived from the values of our other two IDs, instead of just being an ID which is generated somewhat randomly. So to do this, we need to pass in to our callback a function that is going to define the primary key as a composite primary key based on the user ID and the post ID. So we're going to use the primary key function, which is imported from Drizzle. We're going to then return, and we will say user post table, and then we are going to return an ID, which is going to be a primary key and have columns of the user post table dot post ID and the user post table dot user ID, like so. So we now have the primary key, which, as you remember, everything needs a primary key, but this primary key is going to be unique and it's going to enforce that. So if we were to try and add this second record connecting Tim to Next.js 4.2, it would have the same author ID and the same post ID, and it would violate our uniqueness constraint and therefore block us from adding two duplicate records in the many-to-many relation. Go ahead and push those schema changes to your database, and then grab a user ID and a post ID, and we will try this relationship out. So we can go to user posts, add record, put it in our user ID. As you can see, those prefix IDs make it easy to not mix up your user ID and your post ID. Go back, grab your post, and then you can save it. And then we can see we have the post, test post, and the user is me. Then if we wanted to add a second author to this same post, can go get that other user ID and go to our user posts, add record of that user ID, and copy the post ID. And of course, we could also add different posts and have me be the author on multiple posts, but also to show you that our uniqueness constraint on our primary key is being enforced. If we try and create a new relationship, a new user post with that same user ID and same post ID and hit save, it will block us from doing that so that we know we're not going to have that relationship defined in a redundant and inconsistent way. And there we go. That is all for today's lecture. As a recap, we gave a little bit of an overview of decisions you might consider when choosing a database, why it makes sense to use an ORM like Drizzle, and the specific benefits of Drizzle ORM. And then we showcased modeling a complete database schema with one-to-one, one-to-many, and many-to-many relations. If you want, you can implement yourself relationships between users and comments, and add any other additional data you might want to things like posts, such as a post title, post category, and we will pick up this schema later in the next videos when we show you how you can actually write Drizzle syntax to select data from your database, insert data into your database, and do lots of other important things. Until then, All the links required for additional resources or timestamps and the links to the lecture starter code will be in the description. Stay tuned and have a good day.